Hello, and welcome to this video on stress and crack growth in fillet welds. To begin with, let me start by sharing the screen so you can follow along with the PowerPoint that I'm going to use. My name is Girish Kelkar, and I am a welding consultant operating as WJM Technologies. Additional information about my consulting business is on the web at welding-consultant.com, and you're going to find this video in my YouTube channel, The Weld Nugget. So today we're going to talk about stress and crack growth in fillet welds. So let me start by showing you a cross section of a fillet weld. This is a T-joint where the two parts have come together as a T-junction, and a fillet weld was made on the left. This weld has been cross-sectioned to show you what it looks like on the inside. And here we can see the fusion zone outlined by approximately by that black line. Other interesting important features of the fillet are the weld toes. The toes are where the front face of the fillet weld blends with the base metal. This is the weld face itself. And at the other side is the weld root. The weld root is the farthest point on the weld interface which has not been welded. So this line of the weld interface along this line, there is no weld, but the front edge of it has been welded. The throat is effectively the shortest distance from the weld root to the outside face. So essentially, if you apply a tensile stress as shown by these two black arrows, as in trying to pull the weld apart, the stress is going to be transferred through this throat as the bottleneck from one component to the other. The weld I've shown does not have any defects on the inside, but could potentially have, say, cracks and porosities, which will, of course, aggravate the situation. So let's look at what happens when we have stress on a mechanical component, which is not of a continuous or single dimension. For example, this is what is called a stress concentration factor. So we are having a component over here with rounded corners. And if we apply a stress, overall stress of say sigma, then what happens is the stress at the corner is going to be twice that. So there is a stress concentration effect based on the geometry. If we have a plate and we have a hole in there and we apply a certain stress of sigma, then the stress at the edges of the hole is going to be 3 sigma. So 3 times the applied stress. So this is a multiplier effect purely based on geometry. And we can have corners or effectively like a corner on fillet welds. We can also have porosities with effectively a hole in the fillet weld. And we will have stress concentration effects, which will locally increase the applied stress and which can cause some yielding. And here are some examples of such features. I'm showing you another fillet weld which looks a little bit different than the one I showed before because it has a different surface profile. And we'll have the two weld toes. And based on this geometry, there could be a stress concentration effect at the toes. So the stress at the toes could potentially will be larger than the overall applied stress on the components. On the right, I'm showing you a cross section of a weld with porosity inside. And here again, there'll be a stress concentration effect when the stress lines flow through the weld from one component to the other component. Another important factor that you need to realize is what is called a stress intensity factor. Now, this is slightly different than the stress concentration factor in the sense that material properties also come into play once we are dealing with features which are like a crack, like a very, very fine separation between two components. So here I'm showing you a crack in a schematic form in a component. And this is an internal crack, so the entire crack is on the inside. You cannot see it from the outside. And the stress at the tip of the crack is going to be many, many times greater than the applied stress. Same is true with the surface crack. Even with the surface crack, the stress is going to be many times the applied stress. So the stress intensity factor comes into play when the defect is a crack with a sharp tip So the difference between the stress concentration factor and the intensity factor is intensity factor comes into play when the feature is such that it effectively is a very, very sharp crack or crack-like feature. And that can be actually a crack itself or the weld root. And I'm going to show you schematics of that later as well. Now, the stress intensity factor is there's a critical element to that. So this is called a critical stress intensity factor, K1C. So the one over here stands for the fact that we are pulling the two components apart. So in a tensile loading. If the loading on the fillet weld would have been shear, then this would have been K2C, which is slightly different formula, but similar sense. So the K1C has a constant over here based on the geometry, stress, and a square root of pi, and A is the dimension of the crack. So now in this formula, we have both the stress as well as the size of the flaw. Now these are the typical stress, and I'm showing you here in the schematic form, the applied stress, the crack of length 2A, and that A goes into this formula, and the overall applied stress goes over here. Now, typical stress intensity values with the units of megapascal square root meter are shown over here. Glass has a value of 1 because glass is extremely brittle, and even the tiniest of the cracks with a very, very simple loads can lead to failure, as I'm sure you are familiar with. So glass has a value of 1. Ceramics have a value of 10. So ceramics are stronger than glass. So that's why the K1C value is greater, even though ceramics are also quite brittle, but their bond strength is much greater than typical glass. So that's why ceramics have a bigger number. Further down, carbon steels, which is our favorite material for welding in most of the times, is when the hardness of carbon steel is 60, which is very, very brittle, almost like a rock. The K1C value is 25. So anything with high carbon, when it goes to 60, the K1C value is fairly low. If the hardness drops to 50, the K1C value is 40. If it drops to 40, HRC scale, Rockwell C scale, and the K1C value goes to 100. So this is an important trend to notice. As the hardness of the steel goes down, the K1C value goes up. And we want a higher K1C value because a higher K1C value means we can apply a greater amount of stress for a given crack, the crack size, and it won't lead to failure. So K1C is the critical stress intensity. Critical stress intensity is once you reach that value, then the crack starts growing and then it is impossible to stop. So that is a critical value where the crack starts growing and leads to failure. Soft alloys are 200, and basically pretty much it's very difficult for the crack to grow in these alloys. So we have to keep in mind, because most of the time we are welding structural alloys where there is some amount of hardness. So what we need to do is when we are welding, we want to try our best to keep the hardness below 40 so that we have high enough stress intensity factor, critical stress intensity factor. Here I'm going to show you a couple of photographs. This is a surface of a weld. This is a linear weld, and you can see a surface crack over here. And here I'm showing you a cross section. Now this particular cross section is the one I showed you before. This particular one does not have a crack, but if it had a crack for different reasons, and there are many other reasons for cracking, if it had a crack, the crack would be somewhere inside crack would be somewhere and looks something like this. We also have the weld root, which is also effectively like a surface crack. We see a sharp point where the root comes to as a junction to the fusion zone, and it effectively also acts like a crack. So weld root is a common in fillet welds because fillet welds very rarely are welded full penetration. So there is always a weld root in most cases. But this can also be true in butt welds. In butt welds, which are partially penetration butt welds, we can also have a high stress point at the edge of the weld in the root side. Now, when we do apply a load and the component has a crack, what are the different ways we can do to reduce the likelihood of crack growth? And that is called toughness. So when we say that the material is tough, that means it has resistance to crack growth. For composites, that toughness usually comes from fiber reinforcements. So if you have a composite, it has a lot of fibers in there, along with some bonding agent, and these fibers act like a resistance to any cracks which can grow. In glass and ceramics, there are some resistance to crack growth based on phase change, but that is not very common. In most cases, there is no uh, resistance to much of a crack growth except for the bond strength of the ceramic itself. But there are some ceramics where at the tip of the crack, there will be a phase change, and that phase change leads to compression at the crack tip, and that actually prevents it from growing. Typically in metals, we don't have that as much. So what we have in metals is the best way we can handle that is to provide crack tip blunting. That means have the material soft enough that when we have very high stress at the crack tip actually blunts in the sense that we have a lot of localized yielding. And now the tip being sharp has now become a blunt tip, and then it is more difficult for it to grow. So we have two different strategies to reduce crack growth. One is to reduce the overall stress, or actually to apply compressive stress, which will actually close the cracks. Or we can change the material characteristics by reducing the hardness of that component. So let's look at how we can reduce the hardness of the weld zone. Hardness is a very common issue in welding of steels. Now, this is true with other components as well, but majority of the issue we come across in hardness is in hardness of carbon steels. And the major reason for hardness in carbon steel is the carbon content. So one of the things we can do is to reduce the chemistry or reduce the carbon content of the weld zone by changing one of the components to a lower carbon version of it, or we can add a low carbon filler. So we can introduce a filler alloy into the weld zone to reduce the hardness of the weld zone, so make it less susceptible to crack growth. If we cannot do any of these, then we sometimes have to resort to preheating. So preheating of the weld reduces the cooling rate. So when you make the weld and it cools down to room temperature, it doesn't cool down very fast, and that helps to reduce the hardness. And if that is not enough, we can do tempering of the welds. And the tempering is done with a post-weld tempering cycle and to reduce the hardness. Now, many of these topics that I'm mentioning over here have already been covered in different videos in the weld metallurgy playlist. So please definitely take a look at those as well. Now, carbon in carbon steels is not the only reason why the welds can be hard. There are other reasons. For example, when you weld dissimilar metals such as nickel and copper, the weld itself does not have any reaction products, but it is actually quite very brittle. And sometimes we have, say, mixtures such as aluminum and titanium, which will actually react and form intermetallics, and these intermetallics are also very brittle. So anything that can lead to excessive brittleness in the weld will make your weld more susceptible to crack growth. So this is from the metallurgy point of view. So now we're going to look at how to change the discussion based on changing the stress. So one of the things we can do, as I had mentioned with ceramics, is if we apply a compressive stress, then it helps to close the cracks. Now, how can we apply compressive stress on a weld? We can do that by producing a convex profile on the surface of the weld. So when a fillet weld has a convex profile and that molten metal cools, it tends to shrink inwards, and it is now trying to occupy a smaller volume, and that produces compressive stresses on the surface of the weld. As opposed to that, a concave profile, when it shrinks at the end of the weld, it actually produces tensile stress on the surface. So a concave profile becomes more susceptible to crack growth because if there's a tiny crack on the surface, we already have tensile stress. On top of that, when you are pulling the weld, it adds some more tensile stress, and that can lead to crack growth under certain circumstances. Let's look at different profiles. Look at the different profiles. This is on the left is a fillet weld with a convex profile. So this profile over here on cooling will have compressive stresses on the surface, which will help to close the cracks. Now, these compressive stresses are reasonably amount, so they're not purely on the surface. They would probably go more than half into the bulk as well. On the right, I'm showing you a concave profile. A concave profile will introduce tensile stress on the surface. And if there's a crack, then it is more likely to grow in that weld. Let's look at some stress analysis or how to think about it. Now, this stress analysis is not about numerical analysis. We're not going to do some math on stress. We're going to think about what exactly can we do to the weld to reduce the stress. We already looked at what we can do to improve the chemistry of the weld to reduce the hardness. Now we're going to look at what we can do to the stress in the weld to reduce the likelihood of crack growth. So here we are looking at again the toes of the weld. The toes, in this particular case, the toes have a nice blending. So there's a smooth transition between the face of the weld and the base metal. So that's a good thing. So that reduces the stress at that transition point. We do have, however, have a concave face on this one. So we are going to have tensile stresses on the face of the weld. So that is a little bit of a risk. We also have a fairly narrow throat over here, and we also have a feature at the weld root, which effectively acts like a crack, even though the weld itself does not have a crack. But there is a crack-like tip right at the edge of the weld at the weld root. And now when we are applying a tensile stress on this weld, based on the fact that the weld is on one side only, that is also going to introduce some kind of a torque into the weld, which will tend to open up that weld root if the stress is high enough. So these are the things we have to change. So we need to have a different profile. We need to increase the size of the throat, and we see if we can eliminate this unwelded portion itself. So what can we do to manage the stress? The first thing we can do, or you can do as a design engineer, is to specify a convex profile on the face of the weld. And you can do that. As a design engineer, you can specify on the drawing that the weld should have a certain profile on the surface, and that requirement will supersede any requirement in the welding specification. So the welding specifications oftentimes will allow slightly convex to slightly concave faces, of course, within limits. But you as a design engineer can override that and be specific on your drawing that we must have a convex profile. And the convex profile eventually will look something like that when properly made with a dashed white line. The second thing you can do is to avoid this weld root. So this high stress point can be avoided if one of the components is fairly thin. Then you can specify a full penetration weld. Now this full penetration weld can be made if it's fairly thin, let's say less than say 3 millimeters of 1/8 of an inch or less. If the component is slightly thicker than that, then you may have to provide a V-groove on the front edge of the weld so that it allows the fusion to go all the way back. And that might require 1 or 2 passes, but you can make a profile which looks like this dashed white line. Now, sometimes the component is much thicker, and in that case, you may have to go from both sides. So you may have to make a V-groove on both sides, make a weld from this side, make a weld from the other side, and potentially have those two welds overlap. So you have no unwelded section in the middle of the along the weld interface, or at least have sufficient weld on both sides that it is preventing. So it is distributing the stress over a larger weld area and prevents the weld from reaching a critical reaching that critical stress intensity effect. Okay. So there are multiple things you can do. You can change the chemistry of the weld to reduce the hardness, and you can change the size and shape of the weld to reduce the tensile stress and also to actually avoid this high stress point altogether if possible. So in summary, External stress is applied practically every weld. Every weld you make is often a structural weld in these cases, and you're going to have some load on it, whether it's a shear load or a tensile load. In this case, I have used a tensile load as an example. And that can be a direct load, like a mechanical load on the weld, or can be indirect loading, such as through pressure changes or thermal expansion during use of that component. The weld geometry can create stress concentration in some locations as well as stress intensity. So the weld is not a homogeneous and a simple shape. So it has stress concentration effects at the toes of the weld. It has stress intensity effect at the root of the weld. In addition to that, there could be porosities and cracks in the weld, which will aggravate the situation. Options include, so what can we do? As a design engineer, you can do is reduce the tensile stress. Now, this can be done by changing the size and shape and profile of the weld, and also to introduce compressive stresses. If you have a positive profile, like a convex profile, when it cools, it's going to have compressive stress. You can avoid the sharp notch at the weld root completely by requiring a full penetration weld, and this can be done with fillet welds as well as butt welds. And of course, if you can change the chemistry of the weld or the process to reduce the hardness, such as say post-weld tempering or preheating. So there are many techniques which you can do to extend the life of your weld if your weld is found to be susceptible to crack growth, leading to a lower life than expected. Well, I want to thank you for your time in viewing this video. If you're interested in learning more about welding and joining, please subscribe to this YouTube channel by clicking the subscribe button at the bottom of your screen. And on this channel, I already have close to 43. I think this will be the 44th video. And they are in different playlists. So there's a playlist for laser welding, arc welding, resistance welding, design, metallurgy, and process. Many of the relevant videos for this discussion you will find in the weld metallurgy playlist. So please definitely take a look at that. And I want to wish you all a happy learning experience for welding, and take care. Thank you.